let's look at algebraic proofs. Now these are some notes on integers and the expressions that we can use for different types of integers that we'll be using in these examples. So the first example says, prove that the sum of 3 consecutive integers is a multiple of 3. Now an integer is a whole number, and any integer can be represented by a letter, say n. So we'll start by writing down n. And now the idea is that we're looking at the sum of 3 consecutive integers. So the word consecutive means one after the other. And so if we were to write down the next integer after n, it would be n plus 1, since that's one more than n. And the next integer after this would be n plus 2, since that's one more than n plus 1. And since we want the sum of these 3 consecutive integers, we're now going to add all of these together. Now if we collect like terms, we can see that we have n plus n, which becomes 3n, and now adding the numbers, we have 1 plus 2, which becomes 3. We can see that both of these terms have a highest common factor of 3, and so if we factorize that out, we then get 3 and then in brackets n plus 1. So this shows that this expression is a multiple of 3 since we factorized the 3 out. And so this proves that the sum of 3 consecutive integers is indeed a multiple of 3. Now the second example says, prove that the product of an even and odd integer is even. Now any even number is a multiple of 2, and so we have that an even integer can be written as 2n. So we'll first start by writing down 2n. Now since we're looking at the product, this word means to multiply. So we now need to multiply 2n with the expression for an odd integer. Now odd integers are always one more than an even integer, and so an odd integer can be written as 2n plus 1. For example, 2 is even, 3 is odd, and 3 is 1 more than 2. So if we're writing the product, we're now going to multiply this by 2n plus 1. So if we expand the brackets now, we have that 2n times 2n equals to 4n squared. Then we have 2n times 1, which equals to 2n. Now since we're trying to prove that this product is even, we need to factorize a 2 out of this expression. We can see that both of these terms have a highest common factor of 2. We get 2 and then in brackets 2n squared plus n. And so since this is a multiple of 2, because we factorized the 2 out, then the product of an even and odd integer is indeed even. Now the final example says, prove that the difference between the squares of 2 consecutive odd integers is never odd. So the first thing we need to think about is what the word difference means. So this means subtraction, and then the squares of 2 consecutive odd integers can be written in the following way. So we know that an odd integer can be written as 2n plus 1. Since we're looking at the square of this, we're now going to square all of this. If we think about odd integers, let's start by writing some down. So 1, 3, 5, 7, and so on. What we notice is that to get from one odd integer to the next one, we always end up adding 2. So 1 plus 2 gives us 3. 3 plus 2 gives us 5. 5 plus 2 gives us 7, and so on. So if we wanted to write an expression for 2 consecutive odd integers, we would then need to add 2 to this expression here. So 2n plus 1 plus 2, which gives us 2n plus 3. And so writing that over here, we now have 2n plus 3. And again, since we're looking at the squares, we're now going to square this. And because we want to look at the difference between these squares, we're now going to subtract these two expressions from each other. Now 2n plus 1 all squared can be written in the following way. So we have 2n plus 1 in brackets and then 2n plus 1 in brackets again. And if we expand this out, we get the following. So 2n times 2n, which equals to 4n squared. 2n times 1, which equals to 2n. Then we have 1 times 2n, which equals to 2n. And then we have 1 times 1, which equals to 1. And if we collect like terms here, we then get that this equals to 4n squared. So 2n plus 2n is 4n, and then we have plus 1. And now we need to think about expanding this bracket. So 2n plus 3 all squared can be written as 2n plus 3 in brackets, and then 2n plus 3 in brackets again. And now expanding this out, we get 2n times 2n, which is 4n squared, 2n times 3, which is 6n, and then we have 3 times 2n, which is 6n, and then we have 3 times 3, which is 9. Now we need to be careful because there's a minus sign here in front of this bracket, and so we're going to write a minus, and then we're going to open up a bracket and write down this expression when we collect like terms. So we get 4n squared, and then we have 6n plus 6n, which is 12n, and then we have plus 9 on the end, and now we're going to close the bracket, since we're subtracting all of this. Now expanding the bracket, we end up with the following. So we have 4n squared plus 4n plus 1, and now we get minus 4n squared, then we get minus 12n, and then we get minus 9. Now we can see that the 4n squares cancel, and now collecting like terms, we end up with 4n minus 12n, which is minus 8n, and then we have 1 minus 9, which is minus 8. Now in the question, we're trying to prove that the difference between the squares of two consecutive odd integers is never odd. So if something is never odd, then it's even, and so in this case we need to factorize a 2 out to show that this expression is even. Now we can see that minus 8n minus 8 has a common factor of 2, and so this can be written as 2, and then in brackets we have minus 4n minus 4. And since we factorized the 2 out, this shows that this is a multiple of 2, and so therefore it's even and never odd. And so this is how you complete algebraic proofs.